Hello, dear learners. I hope you're all well and ready to start into a new module, into a new lecture for battery technology. Today, we will focus on new approaches, on general approaches for sustainable battery production. And I'm happy to be the one to guide you through this today. My name is Bastian Manz. I'm working for Promotion and I'm a consultant working in e-mobility and have been supporting projects in Rwanda and other countries in electric mobility, in setting up new structures, in setting up new ecosystems, in helping companies to advance their mobility products and helping them to find their space in the electric mobility industry. We are conducting these courses together with our partners from WEMI and GIZ, together with the initiative Invest for Jobs, and are looking forward to welcome you all and hopefully see you all throughout the entire series of our courses. So in this lecture, we will highlight the specific importance for sustainability in battery production. We will take also a larger look a little bit on the automotive sector to see where exactly sustainability is missing so far, in which parts. We will highlight the multi-layered aspects of sustainability in battery production. And last but not least, we will identify potential steps and potential measures that can be implemented to increase the sustainability through concrete solutions in battery production. And yeah, to start off, I would like to share here a quote by Dr. Franz Georg Strauss. Dr. Franz Georg Strauss is the chairman of the Association for Commercial and Public Lighting. And he says, sustainability is the only sensible way to tackle the energy crisis. And the energy crisis can be displayed here in this slide with this picture. This picture, as you can see, is a large ocean and there seems to be like a leak of a pipeline. So that is basically a picture of the gas pipeline Nord Stream in the Northern Ocean, in the northern side of Europe. And there has been a leak, or there has been several attacks on this gas pipeline throughout the last 3 years, as this is critical infrastructure. And this resembles or presents basically the energy crisis, at least for us in Europe, as Europe is very dependent on gas imports, in this case from Russia, and so dependent that we witnessed, or Europe witnessed throughout now the war with Ukraine, several energy crises where there were lacks of energy available, where we had to store energy in form of gas, in form of other means throughout the years in order to get us through the winter, because our whole energy supply system is so dependent on gas and especially fossil energies. So this is basically an idea or the way to get rid of fossil fuel dependency, fossil energy dependencies, reach a higher independence of our own, or of Europe's own energy supply by renewable energies, by sustainable energies, that in the end is not only, of course, it's the biggest factor that this benefits the environment, that we can access solar energy, water energy, hydro energy, wind energy, and so on at a certain point for free without having to buy the combustibles. But at the same time, we get in Europe and countries get more independent and are not dependent on imports from external countries, from external partners that can be then critical and dangerous to keep during political tensions, during war situations. So this is basically a picture that describes the energy crisis and the means to solve it. So sustainability is the way to solve the energy crisis, is further on also the way to decrease dependencies in our energy supply and make countries more independent and more resilient to crisis. So having this as a starter, I would like to speak a little bit more now about the climate targets of the Paris Agreement that most of the world has committed to achieve. So to achieve basically these targets, greenhouse gas emissions have to be drastically reduced. So that is a motivation also to look, of course, at sustainability potentials in the battery production sector or in electric vehicle production. We can see this very well here on the left side. This is an example for Germany. On the left side, we can see here the greenhouse gas emissions that were emitted over the last 35 years, more or less. So starting from 1990, then all the way until 2019 and 2030 as kind of the projection what needs to be achieved in order to comply with the Paris Agreement. So we can see here the greenhouse gas emission in equivalent to million tons of CO2 divided in the different sectors of waste management, agriculture, transportation, building, and industry, as well as the energy industry. And we can see here that in 2019, the part of the transportation sector has been roughly about maybe a sixth part of the overall emissions. And to reach basically the target greenhouse gas emissions for 2030, which are in line then with the Paris Agreement, we will still need to reduce the emissions that are emitted in the transportation sector by 42%. So this is here the 42% that you can see. And on top of that, it helps a lot to get a feeling for the impact also of electric vehicles and of battery production, to have a closer look now at the share of the emissions in this transportation sector. And this is here now the chart on the right side. So we can see that Pkw, which are passenger cars, make 60%, around 60% of the shares of the emissions of 2019. Then we have small portion for rail transport. We have a small portion for coastal transport or shipping, and other emissions. National air traffic is also marginal, rather smaller amount. And NKW means basically all commercial vehicles. So these are buses, these are cargo transportations. These are everything basically that has a commercial purpose, and that makes 35%. So interestingly to see here that the transportation sector is mainly divided by the commercial transportation and by the passenger cars in terms of emitted greenhouse gas emissions. And accordingly, this is also then the major ways how to decrease it. So if we want to increase, if we want, or decrease, if we want to make battery production, if we want to make the transportation sector and electric vehicle production more sustainable, we have to then tackle these specific technologies. So as it says here down also below, alongside the reduction of private motorized transport and the strengthening of intelligent mobility solutions, electromobility is the central element here to make this section here, especially for the commercial and the personal passenger cars, more sustainable. Here in the following slide now, we want to have now a closer look on electric mobility itself. So as we are well aware of, especially throughout the last years, electric mobility has been on the rise globally, in Rwanda, in various African countries. You see that as well. A lot of micro-mobility solutions are implemented, so electric 2- and 3-wheelers. Also more electric vehicles are imported. The charging infrastructure is being set up. So we see overall a global trend in electric mobility, and it's definitely rising. And we can see now here on the left side of that chart, basically the total numbers of electric cars that have been sold over the years. Also, this chart shows from 2015 to 2021. So in 2021, already reaching a total amount of 17.4 million cars. We get also here now split a little bit to see how each country or who are the main buyers, or where are the main buyers located. Obviously here China has the biggest factor, so most of the electric vehicles are sold in China. Then we have here US, France, Germany, we see the UK, we see some European countries, Netherlands, Norway, of course, also has a large share of that. So some countries making significant moves on electric vehicles adoptions. And interestingly, we have to also acknowledge at the same time that this enthusiasm has been generated and this enthusiasm has been spread, that at the same time there's also a lot of criticism. And you see here on the right side some headlines, bargaining for the climate. Researchers see electric car as climate polluters, worse than diesel cars. So there has been and there is still a lot of skepticism around electric vehicles. Even though, for example, Stephen Hawking and some other people praise really the electric car as the mean that will help the humanity and us globally to reach sustainability goals. At the same time, there's also a lot of baggage in terms of pollution, which is why also down below it stated then that compared to the combustion vehicle, the electric vehicle carries a larger CO2 backpack. Basically before its use phase, so that meaning the production of electric vehicles is quite emission heavy. that's something to keep in mind. But we will go a little bit deeper into this now throughout the next slides. And here we show you already a little bit how the greenhouse gas emissions of a vehicle are compared between an electric vehicle and also a combustion vehicle. So here you can see on the left side on the axis the greenhouse gas emissions, and then this is measured through a lifetime, through the lifetime mileage. So basically, the more you use it, the further to the right we will get. And we have here now the comparison between electric vehicles and combustion vehicles. So for electric vehicles, we have here the yellow curve, which is kind of a straight line. And for combustion vehicles, we have here this dark blue line. Now, so what is interesting here to see is that the vehicle production itself is of course constant. So that's basically the greenhouse gas emissions that are produced during the production. We have the greenhouse gas emissions that are produced during the battery production, which you can see is significant. It's almost as much as the whole vehicle production. And then we have, of course, throughout the usage, the energy usage that is used for electric vehicles, as well as the fuel consumption that is necessary to fuel basically the combustion vehicles. And what is interesting here to see is really that the electric vehicle starts with a larger greenhouse gas emissions production already from the beginning, which is mainly because of the battery. But over the long time here, the longer you use an electric vehicle, the more sustainable it gets. And yeah, basically we have here the climatic break-even point. That's what you can see here, where basically this line of the greenhouse gas emissions from the electric vehicle cross the line of the greenhouse gas emissions from the internal combustion vehicle. So this is the the climatic break-even point, and yeah, this is reached during the lifetime. But after that point, electric vehicles become more sustainable than internal combustion vehicles. And yeah, now checking a little bit how these greenhouse gas emissions are presented, or basically are turning out. Here on the right side, we see here this CO2 bag, the baggage that we talked about in the slide before. This is basically the life cycle of the components that are going into the electric vehicle. Also, you see here raw material is part, materials and design, the production is part, the transport of the products, in this case of the cells, plays also into the greenhouse gas emissions. The operation makes a very large part here now, and at the end of its life of the electric vehicles, this part, the recycling or the remanufacturing of the batteries, is also like another contributor to greenhouse gas emissions. Yeah, and continuing, another motivation also for more sustainability in battery production or in the transport sectors, as we saw in the slides before, to cope and to reach the Paris climate agreements, are increasing, of course, the production capacity for batteries and for lithium-ion battery cells in particular. And here we have this displayed as the current developments. We can see here on the left side that in 2020 we had around 631 gigawatt hour capacity in production of batteries globally. then that increased over the last 5 years significantly to 2,256 gigawatt hours per year, and it's expected to grow even further to almost 3,000 gigawatt hours per year until 2030. So there's a lot of movement, there's a lot of constructions, and a lot of capacity building in that space happening at the moment. And over the last 5 years, there has been, of course, a lot of constructions and factory buildings happening in China as one of the main suppliers for batteries, but also in Europe. And here in Europe, on the right side, you can see this in a little bit more detail. So here are basically all battery cell production sites or site projects that have been announced, that have been built already, including their estimated production capacity. So that's very interesting. Make sure to have a look, either pause the video, go a little bit more in detail into the graph, or also feel free to check out the original post at batterynews.com. There we also included more maps of different locations of North America, of Asia, of recycling, and so on. So that will give you a lot of valuable insights. Moving forward, yeah. So now, after seeing basically the movements and the developments in battery production globally, seeing also a little bit how sustainability impacts electric vehicles and how much greenhouse gas emissions are still emitted, what approaches can be used now to make battery cell production more sustainable in Europe. And we want to start with this topic by firstly having a look at some definitions. So what does sustainability actually mean? Also, that, as you can see here, the definition of sustainability development, the path to sustainability is meeting the needs of the present generation sufficiently without compromising the ability of future generations to meet their own needs. So that is the definition of sustainable development. So keeping in mind how we deal with our resources, how our generation deals with our resources in this world, so that the future generations of our children and our children's children are able to meet with the available resources their own needs. Now, the definition of sustainability is placed below. So, sustainability is a concept that aims to balance human activities with the carrying capacity and depletability of the natural environment and human needs now and in the future. Also, that is basically a similar definition, which also entails the kind of a thoughtful and in this way sustainable usage of capacity of resources concerning and regarding our natural environment and our human needs, so that we are able to cope with this now, so today, and also in the future, meaning for our future generations. So this is kind of the opener. So now we want to dive a little bit deeper into the specific sustainability goals, and by that have a look first. So In this overview, in this slide, we want to now go a little bit deeper into sustainability, clarify the basics. So the topic of sustainability must be viewed from three perspectives. The three perspectives can be seen here in this triangular. It is the economic side, it is the ecological side, and it is the sociological side. So these are three pillars of of sustainability, and the different perspectives. It's difficult sometimes to compare them directly with each other because they entail different different goals, different targets for each other. So this is difficult because they might have a complex relationship. However, it's always important to keep in mind that these are interacting with each other, and especially when creating sustainability strategies for countries, for companies, for even just for yourself in your private surrounding, it's important to be aware that there are interdependencies between these three pillars. So for us, we will now focus on the ecological side of sustainability. As we've described already, and as we've learned already throughout the first slides of this presentation, of this lecture, greenhouse gas emissions are a major factor in battery production, and it's compared to the full vehicle production, it is actually quite a lot. However, it's also interesting to see a little bit the different sources from these greenhouse gas emissions, and especially from and have a look at the studies, what have been basically the focus topics in these studies, and to get like a holistic view on the sources. So here on the left side, for that reason, we've included an overview basically of greenhouse gas emissions. Also here again in CO2 equivalent per kilowatt hour of electric vehicle usage, and we see here of capacity, and we see here a big variance or variety of different studies that show also different outcomes. So we see here it starts basically from, it is basically the lowest value of greenhouse gas equivalent emissions at maybe around 40 kilograms of CO2 equivalent per kilowatt hour. So if your vehicle has 80 kilowatt hours, you have to multiply this by 80 to have the full greenhouse gas emissions for your vehicle, but that ranks up to almost 250 and even above. So there has been also studies that show a larger impact on the greenhouse gas emissions. Keeping in mind that this is coming from the battery side. Also, we have to watch always these overviews and also these results a little bit cautious. Some of these studies have been compiled more than 15 years ago. For example, here that one with Seriksen et al. From 2010. Nevertheless, it's important to keep in mind that over the years the technology has changed, vehicles have become more efficient. Also, electric vehicles are produced in higher quantities, which in the end all affects also the greenhouse gas emissions. What can also influence, besides that, the volatility of such study results are system boundaries, data acquisition, impact categories, or also other assumptions. And also, they give us a good indication that the battery and the emissions, the greenhouse gas emissions from the battery are a major factor, but to make a more accurate statement, we would need to understand really more the details. Now, the potentials for reducing greenhouse gas emissions are subdivided in terms of product and process technologies. So when we now want to look a little bit more onto the battery, we will have to separate. One is, again, the product as it is displayed here on the left side. So there are greenhouse gases emitted with the product itself. So meaning mainly battery raw materials, so the lithium, cobalt, sulfur, manganese, nickel, etc. All these raw materials and critical minerals, raw minerals also, they are mined, they are refined using a lot of energy, and that in turn then emits greenhouse gases or greenhouse gases equivalent. And we can see that here on the left side, especially the raw materials make 63% already, like the major part of the whole product side or product related greenhouse gas emissions. Then additional components like plastics, for example, the separator in the battery, or other electronics that are necessary for the battery, make a good fourth of the overall greenhouse gas emissions. And additionally, some smaller section like that is in the end then the electrolyte or some other greenhouse gases that are emitted on the product side. Then on the right side, again, the process side. So this is interesting. Again, that is the second part of the greenhouse gases that are emitted during or for batteries. That is how the battery is produced. So here we have big portions, for example, for the cell production. We have portion for the waste and, for example, other parts, and also a large portion of 40% is the material supply, cathode and anode, housing and BMS. So basically the material that is being transported to the production side of the battery. So that is a large contributor also on the process side of the battery production. Now, if we understand now that we have product and also a process side of greenhouse gas emissions, we want to now take a deeper look onto the specific sections. So, for example, here we have this whole overview, which is basically the life cycle or value chain of battery production. There are 9 factors in total, which we will now analyze throughout the next sections. We can see here, again, separated into product technologies, here like raw material, product, and also the application. Then below we see the process technologies, so the refining of the raw materials, the processes of the battery production, and finally also the waste that is produced during battery production, We have also here, of course, the transport of these materials. So we will take a look on also how the transport is affecting basically the environment of the different components to the production sites. We will check the recycling factor. So what happens after the first life usage or the second life usage of a battery? How is the recycling affecting also greenhouse gas emissions? And last but not least, we will look at the environment. So let's start now with raw materials for this part. So now going into the factor of raw materials, here we can see that this section offers specifically potential for optimizing greenhouse gas emissions, especially on the part of the cathode. We displayed here now on the left side the status quo, and on the right side we can see the quo vadis, so basically where we expect the developments to go and also which potentials we also see. So yeah, having a look now at the cathode material for nickel, manganese, cobalt 111, we see that cobalt sulfate as a pre-product that needs to be refined and used for the battery production displays the highest share of greenhouse gas emissions with 14%. What is interesting here about is that the main cobalt production and supply currently comes from the Democratic Republic of Congo, and here we see, as this is mainly done in smaller mines without standardized working procedures, without standard health and occupational safety procedures, that this is still also a very greenhouse gas emission heavy mining. And by basically switching now, and we turn here to the Quo Vadis, by now switching to battery cell formats that are using less cobalt, we are kind of minimizing greenhouse gas emissions that are used or that are required then for the material, for the raw material production. But at the same time, we also increase the energy density. So that is quite important, as the electric vehicle industry and the battery industry is always aiming for better and higher energy density in the material. So there's plenty of reasons now to switch rather to higher energy density, use less cobalt, and by this increase also the kind of the ecological footprint and the greenhouse gas emissions that are produced during the raw materials. So the potential for CO2 reduction here is very high in the raw materials, and hence through the setup and through the change to other cell chemistries, this can be achieved. So summarized, we can say sustainable battery production must ensure that raw materials are mined in compliance with labor law and reduced factor of the cobalt content. Now we move to refining, so that is now on the process side of the battery production, and we will have a look on how this is being affected by greenhouse gas emissions. So the factor refining illustrates basically that savings can be achieved in the process efficiency of the material preparation. So here we will have on the left side again the status quo, on the right side the quo vadis, so where the potential lays and how this potential for CO2 reduction or greenhouse gas emission reduction can be achieved. So here we can see on the left side the process from the raw materials to the cathode material. So if you remember that small chart from the slide before, this is now the different process steps. So we can see here the different steps from the different sources, from a salt lake, from a mine, then to the raw materials, lean and crystals, which will then be refined to the lithium product, and finally the cathode material that will be then implemented into the battery cells. The challenge here is that the highest share of lithium reserves are located in South America, especially Chile and Bolivia. In their deserts have a lot of lithium resources. Also in Mexico are larger lithium resources which are not yet used, but that will be used. So the lithium extraction from brines by evaporation requires a long process time. So that's a long process that will have to happen then in Chile and Bolivia and in these countries. And so far only significantly less than 60% of the lithium contained in the brine could be recovered. So we still lose here, due to efficiency reasons, a lot of the raw materials. Nevertheless, how can that be improved? So the reduction of process time. So as we saw here now, up to 18 months, it's a pretty long process time for the extraction. And increase of yield by alternative methods like solvent extraction can have effects on potential CO2 reduction. So here on the left side we can see solvent extraction. So here basically the lithium is extracted using a solvent that is very much faster than the extraction by evaporation that is being displayed here. And how that plays out now in the direct comparison, we can see that here on the potentials. So evaporation over extraction is 95% longer. So extraction through a solvent can be much faster, and also the yield, so basically the output and efficiency is higher. So we can get up to 50% more material. So the potential is really the alternative extraction process, such as the solvent extraction, increases the current low efficiency of the lithium extraction process, and process time can be significantly reduced and the yield increased. So that as a summary, the energy required to extract and manufacture the cathode material can be significantly reduced by alternative process technologies, as shown. We will now move to the product of the battery and have a look at the sustainability in this area. So the factor product requires a little bit more holistic view at all the levels of integration. So status quo at the moment, we can see that here on the left side. So usually the battery cells are assembled into battery modules. These battery modules are assembled into battery systems, and they are then assembled or mounted at the chassis of the vehicles. This is the conventional design of a battery electric vehicle. So this includes several stages, several production steps, assembly steps, and offers huge potential to be decreased through, for example, different vehicle architectures, through different battery systems. But nevertheless, the challenge here remains that the only component of the battery system that contributes to the storage of the energy is really the battery cell. And yet here we have 4 different steps, so additional steps. So the material also required to integrate the battery cells adds weight and volume across all the integration steps, and eventually reducing this weight and the volume are TCAL targets for the vehicle that will produce in the end a shorter production time, that will produce in the end a more cost-efficient vehicle, and in the end also less material, and finally also less greenhouse gases that are emitted throughout the process of these materials. In its operation, it will also decrease the weight. So the fewer materials and the fewer weight we have at the vehicle, the more efficient a vehicle can operate. And in the end, also the more efficient the usage, and also in terms of greenhouse gases and emitted CO2 will be. How will be the quo vadis, or how will be the trends that we will see? At the moment, these are basically 2 main directions that we see are developing at the moment. So growing cell formats is one. We can see that already here in this example with the Tesla cylindrical cell. So on the bottom or inside, there's the 21700 cell, and this has been adapted now to a larger cell, a larger cylindrical cell, which in the end creates also a higher energy density, lower greenhouse gas emissions that are emitted during the production, and a less complex vehicle architecture. And the second part that we see are very promising are cell-to-X approaches or cell-to-X designs. That means in specific that battery cells are more integrated into the vehicle. So that can be, for example, cell-to-chassis. So when the battery cells are not integrated into a battery module, but directly in a pack, or even one step further, directly into a chassis. Also, if we look now here on the left side, if we would, for example, integrate now the battery cells into the system, into the pack, we would skip completely here the battery modules section or this production step. And if it would be even possible to integrate that into a chassis directly, then we can eliminate 2 production steps here. So that has overall, on the product side, a large opportunity to reduce CO2. So moving on now from the product side to the process side of the battery production. Here it's interesting to understand that more than half of the greenhouse gas emissions of the lithium-ion battery are determined really by the process factor, so the production of the battery itself is more than half of the greenhouse gas emissions of the complete battery. Here the different production steps are the major emitters for greenhouse gas emissions. We can see that here on the status quo. Here you can see the energy requirement for the battery cell production, just along with the clean and dry room, where the electrode manufacturing and assembly area takes place. 43% of greenhouse gases are emitted then in the drying room, where the evaporation of solvent after the coating process takes place. 38% of the energy of the greenhouse gases are emitted in this production process overview. And the challenge here is basically the energy requirement of the whole battery cell production, and mainly here the clean and dry room. Also, these are the major energy consumers. So in the end, that's also the major emittators for greenhouse gases. Conventional process technology have rather low efficiency, and so that is basically the challenge here. The quo vadis is that process innovations in battery cell productions are implemented more often in, for example, mini environments or in adjusted drying environments. So mini environments reduce the volume by up to 56% and minimize basically also the human impact. The innovative drying technologies, so not looking at conventional, looking at advanced and newer technology, newer equipment, reduces energy consumption and energy requirements by up to 85%. So that is significantly, as we can see now, in relation now also to the consumption here. And additionally, the use of solvents can also be reduced and avoided. So we see basically here a large potential by new equipment, by new production machines within the cell area. So summarized, this can be said, the energy demand of production can be reduced efficiently or a lot by efficient manufacturing processes and an optimal planned operation strategy. Looking now on the application side, here the different usage phases of service life of the battery have significantly influence on the application factor for sustainability and for sustainable battery production. So left side again here the status quo. We can see the usage cycle of a battery, or the usage life of a battery, having the first life approximately the first 10 years, second life the second 10 years, and then like a remanufactured approach or recycled approach after then that stage. The challenge in the application fields is that these different fields of application usually offer an increased lifetime for the lithium-ion battery. And after the first life, the battery still has a capacity of 80% mostly. So there's still a lot of potential of the battery that is not used. Also, the challenge is here how to make this battery usable really for the next 10 years and then potentially even afterwards. So how do we best do that is by integrating structures, ecosystems that can process old batteries after the first life and make them reusable for a second life, and afterwards even for a remanufacturing or re-X. That's how we like to call it. And also repurposing, recycling, or eventually, if it's not recyclable anymore, then elimination. There are currently evaluation criteria missing for that. So the battery reuse that industry is developing a lot. And these evaluation criteria are being developed as we speak. There are global showcases and pilot companies, pilot projects that are kind of pioneers in these areas of second life applications. PEM also has done a lot of work in Germany for using, for example, for example, batteries from automotive vehicles that will be repurposed for second life battery energy storage systems. So that is one application now, but certainly there are more ways how to keep using batteries after the first life. Yeah, so summarized, we can say by extending the service life and improving the ability to disassemble, the sustainability of the battery can be improved, and eventually this can be then also or can affect then the greenhouse gas emissions in the long run. Moving on now, we mentioned it shortly already. Waste is also a big part of the process, especially in the production. Here, it's interesting to have a closer look at the scrap factor of the battery cell production. So basically, how much waste is created through each production step. We see here on the left side the status quo. So here we have a graphic that shows the number of process steps in battery cell production. Minimal 15 production steps, and then the yield per step. So that is basically the production rate, if you will. So how many percent of the products that are set to produce will be produced, and in the end then how much waste is created. Also, this shows that if we have yield per step, if for example 99% is our yield, so 99% of the products are also being produced, then if we have 15 production steps, we will end up with a waste of 14%. If now, for example, the 99%, which is a very high yield per step, is not achieved, and we have maybe 97 or 95, the waste in the end will add up in these 15 production steps up to 37% for 97% of yield per step, and up to 55% of waste if we have a yield per step of 95%. So the key message is here that the more efficient each production step is, the less waste is produced. The more efficient and the higher quality each production step has, the less waste is produced. So the challenge here again is the battery manufacturing process is divided into many different process steps, and the quality evaluation is only possible at the end of the process chain to really then see how much waste really is. So along the process chain, the waste ratio scales up. And what might be the potential here for that? Now looking at Quo Vadis. The potential are quality measures in traceability, or basically including more supervision in the electrode production, in the assembly, and in the cell finalization. Also, digital and smart process strategies really help to illustrate these dependencies and by basically creating better traceability of inefficiencies, of quality issues through digital and smart process strategies, we can in the end reduce the waste and recover more material along the process chain. Yeah, here again, this is summarized. And finally, we will come now to the recycling. So after the lifetime, cells contain a high added value and which must be utilized through efficient recycling process, so that as much as possible of these materials that are still contained in the battery cells can be recovered and can be used. And here on the left side is the status quo again, and it shows pretty precisely that the biggest value share is basically laying in these raw materials like nickel, cobalt, manganese, and lithium. So of the whole battery system, this is quite a huge proportion of this. So the main target or the target is basically to recover as much as possible of these materials to have also the biggest value, or to recover most of the value of the battery. Also 15% of the gravimetric material, which is now here, this part, so 15% of the materials make here this nickel, cobalt, manganese, and lithium, but these account for about 80% of the value share of the battery. So the current recycling processes at the moment are not recovering too much, so only a small proportion of these active materials are recovered. In the end, the high value share is not exploited, so here lies big potential in the future to use more efficient recycling processes that can recover more and more materials. And here on the left side, you can see in this overview different recycling processes, deactivation, disassembly, pyrolysis, mechanical reconditioning, pyrometallurgy, and hydrometallurgy. We're not going to go now too deep into the recycling processes. However, the key message here is that the most of the value of the active materials, of these high value materials, are recovered through the hydrometallurgy, and this is a huge potential, especially to process and to allow higher proportions of these active materials to be recovered. Moving on now, we move now from the recycling to the transport section and getting closer to finishing here this battery value chain. And let's see what the transport part means for greenhouse gas emissions. So the transport is extremely significant, as at the moment battery materials have a long transport way to and within the different countries and globally to reach the different production plants, to reach the refineries, or whatever it may be. So at the moment, these materials travel a long distance for the refining. You can see that here in this map. So, for example, cobalt is coming from Congo, from Australia, is being processed then in Finland, then or will be refined then in Finland. A lot of here nickel, for example, is coming from Indonesia, I think, is then going to Japan. Here mangan also from Australia to India to South Africa to Europe. So there's a lot of production ways and a lot of ways, transport ways, where these materials are polluting and emitting a lot of greenhouse gases. So, and especially for the cells from Asia, the cell manufacturers are shipping then their cells to Europe, system manufacturers, and that causes a lot of greenhouse gas emissions. The potential here is, of course, build local capacities, or build local production sites in Europe, in North America, so that the cells are being produced locally, not in Asia, and that we don't have to transport these, but that are produced locally. Another thing is reusable packaging systems. Also, until now, battery cells are transported in disposable packages, but to save more CO2, save more greenhouse gas emissions, it would be good to have at one point reusable packages. In summary, European cell production can significantly reduce CO2 consumption through short and sustainable transport routes. For this, the extraction and refining of the materials must also be integrated in Europe. And that is basically the summary. And last but not least, let's have a look at the environment factor in sustainable battery production. So in its value chain, the share of renewables in the environment plays an essential role for the life cycle assessment of lithium-ion batteries. And why is that? That is especially why, or the reason for that is specifically because battery cells are produced in countries with a high share of fossil fuels. You can see that here in China, in Europe, in the US, in India, no? Because eventually battery cell production is very energy demanding. So the energy demand for the production determines the costs and the greenhouse gas emissions for the battery. So in the end, low energy prices or a lot of available energy is really key to maintain a profitable battery production. And the current production countries have a low energy cost. No? So that is, for example, as shown here below or above in this graph here. So at the moment, there's also no pressure to reduce kind of the energy demand also of the production steps. So as we saw, the production of especially the process steps of cell production can be very energy demanding. However, as the energy costs now in these countries, in the main producing countries, are very low, there is no specific benefit or not a pressuring benefit to reduce the energy consumption even more. What is the potential in the field of the environment factor? It is basically that European cell production reduces the greenhouse gas emissions by increasing the share of renewable energy in the electricity mix. Also by including more renewable energies, we also affect, obviously, the greenhouse gas emissions of the production of battery cells. And additionally, self-sufficient supply of renewable energy to battery factories can even further reduce the greenhouse gas emissions. So connecting really battery production plants or creating the infrastructure for the battery supply, for the energy supply at battery production sites to be fueled with renewable energy has a significant factor and impact onto the greenhouse gas emissions. So In summary, we can say that the electricity mix in many EU countries is lower in CO2 than the electricity mix in previous cell production countries. Also, in Europe, we have already a little bit more renewable energy integrated, but 100% supply with only renewable energies can be achieved through production-related supply, specifically for battery cell manufacturing plants. Yeah, and here in summary, I would like to conclude this lecture. In the value chain of cell production, there are many CO2 and greenhouse gas emission potentials that we have to realize, that have to be implemented in the medium and long term. The essentials include the reduction of energy requirements during the production, the use of renewable energies, and the improvement of the battery life, and last but not least, to sealing the material cycle through efficient recycling methodologies. What can be actions and recommendations that can be derived out of this? For example, data acquisition. Product and production data must be able to be recorded along the value chain and analyzed anonymously. So creating more transparency as well, establishment of a platform for transparency of energy use and emissions of battery factories. Quick hint here, we have some initiatives in Europe, for example, the battery passport that creates this exact transparency to make it more understandable how much impact the different production steps of the battery value life chain affect the greenhouse gas emissions. And last but not least, the eco-design guidelines, the introduction of a European label for the use of battery cells in electric vehicles. Of course, this needs to be aligned with regulatory measures and economic incentives that need to be realized, that need to be realized to also tackle these potentials. So like this, the European battery cell production offers the opportunity to enforce sustainability requirements and standards. However, we also need to implement now these different actions and work on these recommendations. So eventually, this lecture should have learned you or should have taught you in these 3 ways. I hope you have now a better understanding of the impact of the battery value chain on the different segments and what they mean for greenhouse gas emissions. So it should have highlighted the special importance of sustainability in battery production in Europe, also giving you a little bit of context into the global battery production. It should have provided you the potential for CO2 reduction in these 9 aspects along the entire value chain. So that's what we spent now most of the time on, checking on the product side and also checking on the process side, which are the different aspects that affect the greenhouse gas emissions. I hope that created a good understanding for you. And finally, we discussed which measures can promote sustainable battery production. Yeah, thank you a lot for your attention. I hope you found that session insightful and that you could take some learnings with you for your careers, maybe for your surroundings, for your ecosystems, wherever you are located in Africa, Rwanda, and wherever it may be. Hope you could learn something, and I look forward to see you in our next session.